Hello and welcome to this video on SystemVerilog Arrays. SystemVerilog Arrays are a powerful data structure that allows you to store and manipulate multiple values of the same data type in a single variable. Arrays can be used to represent a wide range of data structures, from simple lists to more complex data structures like matrices or graphs. In this video, we will explore the basics of SystemVerilog Arrays, including how to declare and initialize arrays, how to access individual elements within an array, and how to perform operations on arrays. So let's dive in and get ready to learn some exciting stuff about arrays. Don't forget to like and subscribe to our channel for more informative videos like this. Let's get started. We will also look at some advanced features of SystemVerilog Arrays, such as fixed-size arrays, packed and unpacked arrays, dynamic arrays, associative arrays, multidimensional arrays, and queue. These features can be incredibly useful for modeling complex systems and data structures. So whether you are new to SystemVerilog Arrays or looking to expand your knowledge, this video has something for you. Let's dive in and start exploring the world of SystemVerilog Arrays. What are arrays? Arrays are a way of grouping related variables together. An array is a collection of elements of the same data type that can be accessed using a common name and an index. To create an array in SystemVerilog, you first need to specify the data type of the elements in the array, followed by the name of the array and the size of the array. Here is an example. This code is an example of using an integer array in SystemVerilog. An array is a collection of elements of the same data type, and it can be used to store multiple values in a single variable. In this code, we declare an integer array called myArray with a size of 4, which means it can store 4 integer values. We then use an initial block to initialize the elements of the array with the values 10, 20, 30, and 40. This means that myArray 0 is assigned the value 10, myArray 1 is assigned the value 20, myArray 2 is assigned the value 30, and myArray 3 is assigned the value 40. Finally, we use $display statements to display the values of each element of the array. The %0d format specifier is used to indicate that we want to display the values as decimal integers. Overall, this code is a simple example of how to use an integer array in SystemVerilog and how to initialize and display the values of its elements. SystemVerilog supports a variety of arrays that can be used to store multiple values of the same data type. Here are some examples. int array 1, 6. This is an example of a fixed-size single-dimension array. It is declared as an integer array called array1 with a size of 6 elements. int array 2, 5 down to 0. This is another example of a fixed-size single-dimension array. It is also declared as an integer array, but with a size of 6 elements. The difference is that the index range is specified as 5 down to 0, which means that the array indices range from 5 to 0. int array 3, 3 down to 0, 2 down to 0. This is an example of a fixed-size multi-dimension array. It is declared as an integer array called array3 with a size of 4 rows and 3 columns. The first dimension is specified as 3 down to 0, and the second dimension is specified as 2 down to 0. Bit 7 down to 0, array 4, 2 down to 0. This is an example of an unpacked array declaration. It is declared as a bit array called array4 with a separate 3 registers of each element is an 8-bit value. Each register is of 24-bit. Bit 2 down to 0, 7 down to 0, array 5. This is an example of a packed array declaration. It is declared as a bit array called array 5 with a group of 3 registers of size 24-bit and each register is of 8-bit wide. Bit 2 down to 0, 7 down to 0, array 6, 3. This is an example of a mixed packed and unpacked array. It is declared as a bit array called array 6 with a size of 3 elements. Each element is a 3-row by 8-column bit array. Overall, these examples show some of the ways that arrays can be declared and used in SystemVerilog. Different array types and sizes can be useful for storing and manipulating data in different ways, depending on the requirements of a particular design. A fixed-size array is a data structure used to store a collection of elements of the same data type, where the size of the array is determined at the time of declaration and remains constant throughout the simulation. Fixed-size arrays can be single or multidimensional, and elements can be accessed using index values. They are commonly used to implement algorithms and data structures, and are initialized with default values of 0. In fixed-size array we have 2 types. First, single-dimensional array. Second, multidimensional arrays. Let's start with single-dimensional arrays. We can declare a single-dimensional array in 2 ways. The compact declaration is simply an integer array followed by the size of the array in square brackets. For example, int array 1, 6 declares an integer array of size 6. The verbose declaration, on the other hand, specifies the size range of the array. For example, int array 2, 5 down to 0, declares an integer array of size 6 with indices ranging from 5 to 0. Now, let's move on to multidimensional arrays. Multidimensional arrays are an array of arrays. We can create a 2-dimensional array with the syntax intir 2, 3. This array has a total of 2 times 3 equals 6 elements. A 2-dimensional array is an array of arrays. The array are with dimensions 2 times 3 means that there are 2 rows and 3 columns. To represent this array in a table, we can list out the rows and columns and fill in the values at each index. The first row of the table represents the columns, labeled as column 0, column 1, and column 2. The second row of the table represents the indices of the first dimension, labeled as row 0 and row 1. Starting with the first index 0, 0, we can fill in the value of this index under row 0 and column 0. Similarly, we can fill in the values for the other 5 indices of the array in the corresponding cells of the table. This table helps to visualize the arrangement of data in a 2-dimensional array and allows us to easily access and modify its elements. Similarly, we can create a 3-dimensional array with the syntax intir 2, 2, 2. This array has a total of 2x 2x2 is equal to 8 elements. In this table, we have a representation of a 3-dimensional array called with a size of 2 by 2 by 2. The table has 2 rows and 2 columns in each of the 2 layers, making a total of 8 elements. Each cell in the table represents an element in the array. The first index of the array represents the layer, the second index represents the row, and the third index represents the column. For example, 0, 1, 1 represents the element in the first layer, second row, and second column. Similarly, 1, 0, 0 represents the element in the second layer, first row, and first column. We can declare a two-dimensional array with a size range by using the syntax int array 3 to down to 0, 3 down to 0. We can also assign values to fixed size arrays. For example, we can assign values to array 1, array 2, and array 3 using the following syntax. This code is an example of initializing fixed size arrays in SystemVerilog. The first array, array 1, is a single-dimensional array with a size of 6 elements. It is being initialized with values 0 to 5 using the compact declaration syntax. The second array, array 2, is also a single-dimensional array with a size of 6 elements. It is being initialized with the same values using the verbose declaration syntax. The third array, array 3, is a two-dimensional array with 3 rows and 4 columns. It is being initialized with a 2D array of values using the curly bracket syntax. Each inner set of curly brackets represents a row, and the outer set of curly brackets represents the entire 2D array. In this case, the first row has values 0 to 3, the second row has values 4 to 7, and the third row has values 8 to 11. Finally, we can manipulate fixed size arrays using loops. We can use a for each loop to iterate over each element of a single-dimensional array, while a for loop is useful for iterating over each element of a two-dimensional array. In the video, we provide an example code to demonstrate how to manipulate arrays using loops. In this code, we declare 3 fixed-size arrays of different dimensions, array 1, array 2, and array 3. Array 1 is a single-dimensional array of size 6, initialized with values from 0 to 5. Array 2 is also a single-dimensional array of size 6, but it is declared using the verbose syntax. The values are initialized in the same way as array 1. Array 3 is a two-dimensional array with 3 rows and 4 columns. It is initialized with values using nested braces. We then print out the values of each array using a for loop. The loop iterates over each element of the array and prints its value. In this output, we have 3 arrays, array 1, array 2, and array 3. Array 1 and array 2 are one-dimensional arrays that contain integers from 0 to 5, with each element assigned to a specific index. Array 3 is a two-dimensional array that contains values from 0 to 11 arranged in 3 rows and 4 columns. The values are assigned to specific indices within each row and column. The values in array 1 and array 2 are assigned directly to each element using an initialization list, while the values in array 3 are assigned using nested initialization lists. Packed and unpacked arrays are two different ways of representing digital signals in digital design and computer programming. In a packed array, multiple elements are packed together into a single identifier. On the other hand, in an unpacked array, each element is assigned a separate identifier and can be accessed individually. The choice between packed and unpacked arrays depends on the specific requirements of the design or programming task. Unpacked arrays are useful for managing individual signals, while packed arrays are used for managing groups of signals. Now, we will explore the differences between packed and unpacked arrays in more detail and discuss when to use each type. We will also provide examples to help illustrate the concepts and give you a better understanding of how they work. Let's start with a closer look at packed arrays. Packed array is a data structure that efficiently stores and retrieves arrays of fixed-length elements by packing them tightly in memory without any gaps. Instead of using separate memory locations for each element, packed arrays store all the elements in a contiguous block of memory. This code declares a packed array called array5 using the bit data type. The first set of square brackets, 2 down to 0, specifies the group of 3 registers. The second set of square brackets, 7 down to 0, specifies the 8-bit registers. Since this is a packed array, the memory for this array will be allocated in a contiguous block. The total memory size required for this array will be 24 bits, 8 elements asterisk 3 bits per element. The memory will be allocated in row major order, which means that the first row will be stored first, followed by the second row, and so on. Within each row, the first element will be stored first, followed by the second element, and so on. So the memory allocation for this packed array would look like a continuous block of 24 bits, with the first 8 bits representing the first element in the row, followed by the next 8 bits for the second element in the row, and so on until the last 8 bits which represent the last element in the row. Overall, the table gives us a visual representation of how the memory is allocated for the packed array and how each element can hold multiple bits of data. Now, we will explore what unpacked arrays are and how they are used in SystemVerilog. Definition: an unpacked array is a type of array in SystemVerilog that allows you to store and manipulate a collection of values. Unlike a packed array, which is a fixed-size array that stores multiple values in a single memory location, an unpacked array is a dynamically sized array that stores each value in a separate memory location. Unpacked arrays are useful when you need to store a variable number of elements, or when you need to access individual elements of an array independently. They are often used in SystemVerilog for tasks like storing and manipulating sets of configuration data or for storing the results of simulations. This table represents an unpacked array named array4 that can hold 8 elements. Each element of the array is an 3-bit bit vector i.e array4 0, array4 1, array4 2, which means it can store binary values with a fixed length of 8 bits. The table shows the binary representation of each element of the array, with the most significant bit, MSB, on the left and the least significant bit, LSB, on the right. The syntax for declaring an unpacked array in SystemVerilog includes the data type, the name of the array, and the range of indexes that the array can hold. In this code, the data type is bit 0 down to 2, which specifies a 3-bit bit vector. The name of the array is array4, and the range of indexes is 7 down to 0, which means the array can hold 8 elements with indexes 0, 1, 2, 3, 4, 5, 6, and 7. In conclusion, the table we looked at represents an unpacked array named array4 that can hold 8 elements, and each element is an 3-bit bit vector. This table is a useful tool for visualizing how unpacked arrays are organized in SystemVerilog, and it's essential for understanding how to work with arrays in SystemVerilog. Now, we will talk about dynamic array. A dynamic array is one dimension of an unpacked array whose size can be set or changed at runtime. This means that the space for a dynamic array doesn't exist until the array is explicitly created at runtime. This is in contrast to a static array, where the size is fixed at compile time. To declare a dynamic array in Verilog, we use an empty word subscript after the array name, like this. Data underscore type array underscore name. Here, data underscore type is the data type of the array elements, and array underscore name is the name of the array. To allocate space for a dynamic array at runtime, we use the new operator like this. Array underscore name is equal to new data underscore size. Here, data underscore size is the number of elements to be allocated in the array. The new operator allocates memory for the array elements and returns a pointer to the first element of the array. Dynamic arrays are useful for situations where the size of the array is not known at compile time or may change during the execution of the program. However, they do have some overhead in terms of memory allocation and access time, so it's important to use them judiciously. Let's start by looking at the example code. We begin by defining a module called dynamic_array_example. Inside the module, we declare a dynamic array called my_array using empty square brackets to indicate that its size can change at runtime. In this module, we have declared a dynamic array called my_array. The use of empty subscript indicates that the size of the array can change at runtime. Moving on to the initial block, we are allocating space for 3 elements in the array using the new operator and assigning values to each element. Here, we have assigned 10, 20 and 30 to the first, second, and third element respectively. Next, we are using a for each loop to display the values of the array. The for each loop is a convenient way of iterating through an array in Verilog. We are using the for each loop to iterate through the my_array and display each element using the $display system task. Finally, we end the initial block and complete the module. Overall, this module demonstrates how to declare, allocate space, assign values, and display the elements of a dynamic array using SystemVerilog. When we run this code, we get the output. Array elements 10, 20, 30. This output shows us that the code is working correctly. We can see that the array has been initialized with the values 10, 20, and 30. And the for each loop is able to iterate over each element and print it out. There are several methods you can use to work with dynamic arrays. First, you can allocate storage for a dynamic array using the new operator. To do this, you declare a dynamic array with an empty subscript and then use the new operator to allocate memory for the array. For example, you can declare two dynamic arrays called the_array1 and the_array2 and then allocate memory for them using the following syntax. Bit 7 o'clock, the_array1. int the_array2. The_array1 is equal to new 4. The_array2 is equal to new 6. In this example, the_array1 is a dynamic array of 4 elements and the_array2 is a dynamic array of 6 elements. Once you have allocated memory for a dynamic array, you can initialize the array by assigning values to each element. For example, you can initialize the_array1 with the values 0, 1, 2, 3 and the_array2 with the values 0, 1, 2, 3, 4, 5 using the following syntax. The_array1 is equal to 0, 1, 2, 3. For each, the_array2 j, the_array2 j is equal to j. Now that you have initialized a dynamic array, you may need to resize it. To change the length of a dynamic array after it has been declared and initialized, you can use the new operator again. For example, you can resize the_array1 to have 10 elements using the following syntax. The_array1 is equal to new 10. In this case, the old values of the_array1 will be deleted and d_array1 will be resized to have 10 elements. If you want to retain the old values of a dynamic array while extending it, you can use the following syntax. d_array1 is equal to new 10 d_array1. This syntax will allocate 6 new elements for d_array1 and retain the values of the 4 old elements. In addition to these methods, there are other methods you can use to work with dynamic arrays, such as the size method, which returns the current size of a dynamic array, and the delete method, which empties the array, resulting in a zero-sized array. I hope this has helped you understand dynamic arrays and the methods. We will be looking at an updated version of the Verilog module called dynamic_array_methods_example, which contains all the dynamic array methods new, size, and delete. In this module, we have declared a dynamic array called my_array with an empty subscript indicating that its size can change at runtime. We then allocate space for 3 elements in the array using the new operator and assign values to each element. Here, we have assigned 10, 20 and 30 to the first, second, and third element respectively. Next, we use the size method to display the size of the array. The size method is used to retrieve the number of elements currently allocated for the array. In this case, it should return 3. After that, we use a for each loop to display the values of the array. We are iterating through the my_array and displaying each element using the $display system task. Moving on, we free up the memory allocated for the array using the delete operator. The delete operator is used to release the memory previously allocated for a dynamic array or object. Finally, we use the size method again to display the size of the array after deletion. In this case, it should return 0 since we have deleted the array and released all of its memory. Now, we are going to talk about queues. A queue is a variable size, ordered collection of homogeneous elements. Similar to a dynamic array, queues can grow and shrink in size, and they support adding and removing elements anywhere within the queue. To declare a queue in programming, you need to specify the data type of the elements you want to store and give the queue a name. The syntax for declaring a queue in most programming languages looks like this. Data_type queue_name $. Let's break it down. The data_type refers to the type of data you want to store in the queue, such as integers, characters, or strings. The queue_name is the name you give to your queue, and you can choose any name that makes sense to you. The $symbol indicates the maximum size of the queue, which can vary depending on the programming language. Here is an example of how to declare a queue. In this code, we first declare an unbounded queue of integers called my_queue and initialize it with the values 1, 2, 3, 4. Next, we add an element to the end of the queue using the push_back method. This method adds the value 5 to the end of the queue and increases the size of the queue to 5 elements. Finally, we remove an element from the front of the queue using the pop_front method. This method removes the first element in the queue, which is the value 1, and assigns it to the variable front_len. We then print out the updated queue using $display, and also print out the value of the front element that was removed. The output of this code will be the first $display statement prints out the updated queue after we added an element to the end using push_back. The updated queue now has the values 1, 2, 3, 4, 5. The second $display statement prints out the updated queue after we removed the front element using pop_front. The updated queue now has the values 2, 3, 4, 5. Finally, we print out the value of the front element that was removed, which is 1. There are two types of queues, bounded and unbounded. A bounded queue has a fixed maximum size, which means that once the queue is full, you can't add any more elements to it. An unbounded queue, on the other hand, can grow dynamically to accommodate any number of elements. Let's take a look at an example of how to declare a bounded queue in SystemVerilog. int my_queue declares an empty bounded queue of integers. In this example, we have declared an empty queue called my_queue that can store integers. The symbol indicates that this is a bounded queue, but we haven't specified a maximum size yet. To specify a maximum size, we can add a number inside the brackets, like this. int my_queue 10 declares a bounded queue of integers with a maximum size of 10. Now, we have specified that the maximum size of my_queue is 10. Once we add 10 elements to the queue, we won't be able to add any more. Now, let's take a look at an example of how to declare an unbounded queue in SystemVerilog. Bit 31, 0, my_queue declares an empty unbounded queue of 32-bit integers. In this example, we have declared an empty queue called my_queue that can store 32-bit integers. Because we haven't specified a maximum size, this is an unbounded queue that can grow to accommodate any number of elements. Queue data type provides a set of methods to work with it. One of the most basic methods is size. This returns the number of items currently in the queue. Another important method is insert. This allows you to insert an item into the queue at a specific index position. You provide the index position and the item you want to insert. This is useful when you need to insert an item in the middle of the queue instead of at the beginning or end. Delete is another method that you can use to remove an item from the queue. You provide the index position of the item you want to delete. Push_front and push_back are methods that allow you to insert items into the front or back of the queue, respectively. These methods are useful when you want to add items to the queue without worrying about the index position. Pop_front and pop_back are methods that allow you to remove the first or last item from the queue, respectively. These methods are useful when you need to process items in order and want to remove them from the queue as you process them. Let's look at the code. The module starts by declaring three arrays J, B and Q. The J array is initialized to the value 1, the B array is initialized with two elements 3 and 4, and the Q array is initialized with three elements 0, 2, and 5. These arrays are used to perform various operations on the queue. Moving on to the initial block, the code performs several operations on the queue using built-in methods of the queue data type. First, it inserts the value 1 before the element at index 2 using the insert method. This changes the queue from 0 to 5 to 0, 1 to 5. Next, it deletes the element at index 1 using the delete method. This changes the queue from 0, 1 to 5 to 0 to 5. Then, it inserts the value 6 at the front of the queue using the push_front method. This changes the queue from 0 to 5 to 6, 0 to 5. After that, it removes and assigns the last element of the queue to j using the pop_back method. This changes the queue from 6, 0 to 5 to 6, 0 2 and the value of j becomes 5. Then, it inserts the value 8 at the back of the queue using the push_back method. This changes the queue from 6, 0 2 to 6, 0 to 8. Next, it removes and assigns the first element of the queue to j using the pop_front method. This changes the queue from 6, 0 to 8 to 0 to 8 and the value of j becomes 6. Finally, it displays the contents of the queue using the for each loop and the $display statement, which prints each element of the queue on a new line. At the end of the simulation, it deletes all elements from the queue using the delete method, which changes the queue from 0 to 8 to an empty queue. Running the simulation produces the output of 0, 2 and 8, which are the elements of the queue that were displayed using the $display statement. Let's start with associative arrays. Associative arrays are a data structure that's useful when the size of the collection is unknown or the data space is sparse. One of the benefits of using an associative array is that it doesn't have any storage allocated until it's used. This means that memory isn't wasted on unused elements, which is especially useful when working with large collections of data. Another advantage of associative arrays is that the index expression isn't restricted to integral expressions. It can be of any type, which makes it more versatile than other array types. This allows us to create arrays with string indexes, for example, which can be very useful in certain situations. The syntax for declaring an associative array is similar to that of other arrays, with the addition of the index type in square brackets. The general format is data_type array_name, index_type. The data type specifies the type of value that the array will hold, and the index type specifies the type of the index. For example, let's say we want to create an associative array to store the ages of a group of people, with their names as the index. We would declare it like this: int agelist string. Here, the data type is int, which means the array will hold integer values. The index type is string, which means we will be using strings as the index. It's important to note that the index type can be of any type, not just integers. This makes associative arrays more flexible than other array types. To summarize, the syntax for declaring an associative array is data_type array_name, index_type. The data type specifies the type of value the array will hold, and the index type specifies the type of the index. Let's look at the code. We start by declaring a module called associative_array_example. Inside the module, we declare an associative array called car_stock of integer type using square brackets with the index type as string. This means that we can use strings as the index to access elements of the array. In the next block of code, we add some cars to the stock using curly braces in an initial block. This means that these values will be initialized when the simulation starts. We set the value for the red car to 5, the value for the blue car to 7, and the value for the green car to 3. Finally, we use another initial block to print the values of the elements in the array using the index. We use the $display statement to print the values to the console. We print the number of red, blue, and green cars stored in the array. When we run this code, the output will show the number of cars of each color stored in the associative array. The output will be number of red cars, 5. Number of blue cars, 7. Number of green cars, 3. Associative arrays are a powerful tool in SystemVerilog that allow us to store and access data using flexible indices, which can be particularly useful when the size of the collection is unknown or the data space is sparse. Associative arrays have many built-in methods that make it easier to manipulate the data stored within them. Here are some commonly used methods. Num. This method returns the number of entries in the associative array. For example, if we have an associative array called ex_array, we can find out how many entries are stored in it by calling ex_array.num. Delete. Index. This method removes the entry at the specified index. For example, if we want to remove the entry stored at index 3 in the associative array ex_array, we can call ex_array.delete 3. Exists. Index. This method checks if an element exists at the specified index. If an element exists, it returns 1, otherwise it returns 0. For example, if we want to check if there is an element stored at index 5 in the associative array ex_array, we can call ex_array.exists 5. First, var. This method assigns the value of the first index in the associative array to the variable var. For example, if we want to assign the value of the first index in the associative array ex_array to a variable called first_index, we can call ex_array.first, first_index. Last, var. This method assigns the value of the last index in the associative array to the variable var. For example, if we want to assign the value of the last index in the associative array ex_array to a variable called last_index, we can call ex_array.last, last_index. Next, var. This method assigns the value of the next index in the associative array to the variable var. For example, if we want to assign the value of the next index after the current index to a variable called next_index, we can call ex_array.next, next_index. Prev. var. This method assigns the value of the previous index in the associative array to the variable var. For example, if we want to assign the value of the previous index before the current index to a variable called prev_index, we can call ex_array.prev, prev_index. These are just a few examples of the many built-in methods available for associative arrays in SystemVerilog. These methods can help make it easier to manipulate data stored within an associative array and make it a powerful tool for storing and accessing data. We will look at an example code that uses all the associative array methods num, delete, exists, first, last, next, and prev. We will also see the output of this code. Let's take a look at the code. This code demonstrates the use of associative array methods in SystemVerilog. An associative array is a collection of key-value pairs, where each key is unique and maps to a corresponding value. SystemVerilog provides several built-in methods that allow us to manipulate associative arrays. Let's go through the code step by step to understand how each method is being used. First, we declare an associative array called stock using the string data type for keys and int data type for values. We then add some items to the stock array using the assignment operator, where the key is the name of the item and the value is the quantity. Next, we use the num method to get the number of items in the stock array. This method returns the total number of entries in the associative array. Then, we use the delete method to remove an item from the stock array. This method takes the key of the item we want to remove as an argument and deletes the corresponding key value pair. After that, we use the exists method to check if an item exists in the stock array. This method takes the key of the item we want to check as an argument and returns 1 if the item exists in the array and 0 if it does not. We then use the first method to get the first item in the stock array. This method takes a variable as an argument and assigns the key of the first item in the array to that variable. Similarly, we use the last method to get the last item in the stock array. Next, we use the next method to get the item after a given key in the stock array. This method takes a variable as an argument that holds the key of the current item and assigns the key of the next item in the array to that variable. Finally, we use the prev method to get the item before a given key in the stock array. This method takes a variable as an argument that holds the key of the current item and assigns the key of the previous item in the array to that variable. The output of this code shows the results of each method call. We see that the number of items in the stock array is initially 3, but after removing banana, it becomes 2. We also see that banana does not exist in the stock array. Additionally, we see the first and last items in the array, as well as the items that come after apple and before orange in the array. So, in this video, we covered SystemVerilog's 5 different types of arrays. First, we saw fixed size arrays. These are arrays where the size is predetermined and cannot be changed during runtime. Fixed size arrays are useful when you know exactly how much space you need to store your data. Next, we have packed and unpacked arrays. Packed arrays are arrays where each element occupies the same number of bits, while unpacked arrays allow each element to have a different number of bits. Packed arrays are useful for storing data in a compact form, while unpacked arrays are useful for storing data with varying sizes. The third type of array is the dynamic array. These are arrays where the size can be changed during runtime. Dynamic arrays are useful when you don't know exactly how much space you'll need to store your data. Fourth, we have queues. Queues are a type of dynamic array where elements are added to the back of the array and removed from the front of the array. Queues are useful for implementing FIFO, first in, first out, and LIFO, last in, first out, behavior. Finally, we have associative arrays. These are arrays where each element is associated with a unique key, rather than an index. Associative arrays are useful for storing data where the keys have meaning, such as a dictionary or a phone book. So, when should you use each type of array? Use fixed size arrays when you know exactly how much space you'll need. Use packed arrays when you need to store data in a compact form, and unpacked arrays when you need to store data with varying sizes. Use dynamic arrays when you don't know exactly how much space you'll need. Use queues when you need to implement FIFO behavior, and associative arrays when you need to associate each element with a unique key, and when you don't know exactly how much space you'll need. Thanks for tuning into our video on arrays in SystemVerilog. We hope you found it informative and helpful. If you have any questions or feedback, please feel free to leave a comment below. We love hearing from our viewers and value your input. If you enjoyed this video, please consider giving it a thumbs up and subscribing to our channel. We regularly post videos on digital design and verification, so be sure to stay tuned for more great content. Once again, thank you for watching. This is Jairaj Mirashi signing off, and we will see you in the next video.